Everyone. I hope you can hear me. I'm Avinash Tongre. I'm hosting today's review session. This is lecture 8 by Professor Frank Zok from California, Santa Barbara. And this is going to be on experimental techniques for dynamic deformation of solids. So as we have been doing in the past, if you have any questions before we start discussing based on the lecture that is already there, maybe you had a chance to look at it again. Feel free to write questions in the text box that we can have Professor Zok address. And if not, we can get started with the homework questions that were posted. So Frank, you want to take over?
Yeah, sure. All right. Thank you, Avi. Welcome back, everybody. So at the end of the lecture on Monday, I posted a couple of homework problems. The first was largely conceptual in nature. We recall that we talked about various test techniques, the most common ones, of course, being the Kolsky bar and the plate impact, as well as some other ones that proved to be useful in elucidating the mechanics and the mechanisms associated with certain types of loadings, things like small projectile impact tests. So the first homework problem was to compare and contrast the pros and cons of these three different types of tests. So let's just go through some of the key items here. With the Kolsky bar, this is certainly the most common method that's used. One of the big advantages here is that you have very well-controlled axial loading. You have, as another plus, you have virtually all of the information that's needed to get the loads, the strains, and the strain rates, all from conventional, reliable strain gauges. Okay? So that's a big plus. The one downside to the Kolsky bar is that your maximum strain rate is limited, and that it's limited to about 10 to the 4 per second. Now, I'll say a little bit more about that limitation in just a moment. But 10 to the 4 is the practical limit in many conventionally sized Kolsky bars. It can get higher if you have miniature Kolsky bars and use very small test specimens. So those are the key items there. The plate impact. The big plus here is, well, there are two really. It's that you have well-controlled uniaxial straining. Because you are loading under uniaxial straining, you can also develop very high pressures because of the constraint on plastic deformation. You're essentially deforming the material volumetrically. So this allows you to access very high pressures. People have measured pressures in the hundreds of gigapascals, which are enormous numbers. And you can get to very high strain rates as well, 10 to the 6 per second. Okay. The downside to these tests is that they're difficult to implement. They're expensive to implement. The instrumentation, the gas guns themselves, the systems that are used for measuring backface velocities, these VISAR systems, these are all very expensive propositions. Okay. You probably couldn't get off the ground there, in under $1 million. That's the big downside. The small projectile impacts are useful in a number of situations. They do give us access to more complex loading states and strain paths, ones which we wouldn't be able to attain through the Kolsky bar or plate impact tests. And the nature of the loading states and the strain paths that it allows access to are ones that are relevant to certain important applications, particularly regarding penetration by projectiles, by ballistic threats, generally. The downside to these types of tests is that there's minimal in situ measurement. You can visualize what's happening. We have high-speed photography that can allow us to learn something qualitative about what's happening, but it's difficult to use that information in a very quantitative way. The other thing here that's important to note, which is a bit of a downside, but it's sort of an essential ingredient here, is that in order to interpret the results, you need to make some post-test examinations of your test specimens and perhaps your projectiles as well, and compare those observations with either analytical or computational models of material and system behavior. Okay? And this often involves coupling the projectile with the specimen in the sense that the projectile response will actually depend on the specimen properties. Okay? So that's the downside. Those are the key items. If any of you have other items that you think are important, feel free to shout them out. I can't see the chat box or the question box, so if you want to add something, just feel free to speak up.
Hi, Frank. This is Avi again. I just added a question. How does this compare with laser shocks, which is pushing the strain rates to much higher rates, like 10 power 10 and much smaller samples?
Yeah. You know, the kinds of volumes of material there that you're normally probing are small. Although I'm not familiar with all of the details, my sense is that the interpretation of the data is more complex. If you are indeed interested in applications where those types of rates are present, then of course you have few options to probe the material response experimentally.
That's true.
Yeah.
Yep. Thank you.
Okay, sure. Okay, if there's nothing further, I'll go on to the second problem. This was a fairly straightforward calculation of sorts. And so the problem here, recall, is one in which you have an aluminum bar. It's very long and it's bonded at one end to a long steel bar. They're the same cross section. And then we put a pressure pulse of some magnitude P naught, a constant magnitude, into the aluminum bar at one end, at the free end, for duration of T naught. And that pressure pulse moves down the aluminum bar towards the steel bar. And here you're asked to calculate and sketch the distributions in the stresses along the bar, both at the instant at which the incident pulse reaches the interface and a short time later, in this case, a quarter of the pulse duration time T naught. Okay? So the thing to recognize here is you're going to have to consider both stress reflections and stress transmission at the interface. Because you have two dissimilar materials, you will have dissimilar acoustic impedance, and so the stress will not pass through that interface unchanged. So this is the picture of the stress distribution immediately or at the instant of contact. So on the left side, we have the aluminum, the right side, we have steel. We're assuming here that the length of the aluminum, this isn't too critical, but we're assuming for this illustration that the bar length, the aluminum bar length, is greater than essentially the physical length of the pulse. And that length of the pulse in the aluminum bar is going to be the time duration of that pulse times the wave speed in the bar. Okay? You can see this product has units of length. And so as that pulse is approaching the interface, you have the leading edge of the pulse here moving from left to right, and you have the trailing pulse here also moving from left to right at the same speed. And at the instant that it hits the interface, of course, you have no stress present within the steel. Okay, that's essentially a trivial solution, and it's just a starting point. We recognize, incidentally, that if we have a pressure pulse of magnitude P naught, it's assumed to be constant, the pressure or the axial stress within the aluminum will be constant over this portion of the bar here. So the incident stress is equal to P naught. Now, the second part then is to calculate the stress distribution after some increment of time. In order to do that, you need to dig up a few basic properties of the two materials. Well, all you really need is the modulus and the density, and you can calculate everything else. So the modulus of aluminum, typically about 70 GPa, that of steel about 200. Density of aluminum is about 2.7 grams per cubic centimeter. Density of steel is about 7.8. From those numbers, we can compute two other quantities that are of interest to us. One is the wave speed. This is, recall, just the root of A over rho. So for the aluminum, this turns out to be about 5090 meters per second. For the steel, it's about 5190 meters per second. Note that these two numbers, even though these materials appear very different in terms of their moduli and their densities, exhibit almost the same wave speeds. This is actually true of most structural metals. And the reason for that is if you look fundamentally at the origin of some of these properties, you find that the modulus usually scales linearly with the density, the mass density of the material, such that the ratio of the modulus to the mass density is pretty much constant over the whole range of structural materials. And of course, we're excluding things that are non-structural in nature, things like lead, which has a very high density, but a very low modulus. The other thing we need here is the acoustic impedance. We can couch that in terms of the product of the density and the wave speed. So for the aluminum, it's 13.7 million in the appropriate SI units. That of steel is considerably higher. It's at about 40 million. Okay, so there's a large acoustic impedance mismatch at that interface. And that's what ultimately gives rise to the reflections, the magnitude of the reflections and the transmitted stresses. So we went through and presented some of the solutions that are relevant here. Firstly, to the stress that's reflected at the interface. And this is just the difference in the acoustic impedance, making sure you've got them in the right order. You take the acoustic impedance of the material into which the stress is going, less the acoustic impedance of the material from which the wave is coming. So Z steel minus Z aluminum, and divided by the sum of the two acoustic impedances. And we're doing this all on a normalized basis, so we can write sigma R normalized by sigma I, or equivalently normalize it by P naught, and that ratio becomes 0.49. The transmitted pulse is given by twice the acoustic impedance of the steel, divided by, again, the sum of the two acoustic impedances. And if we normalize that by the incident stress, we get a number of 1.49. Okay? So if we want to represent that result graphically, here it is. So let me just walk through some of these little colored bits. So this dashed line here is the pressure distribution at T equals 0. As we'd noted then, both the front of the wave and the rear of the wave are moving from left to right at some speed, the wave speed in the aluminum in this case. So at some time 1/4 of T naught, then at 1/4 of T naught, the wave would have moved 1/4 of the distance from where it was here at the trailing edge towards the interface to this point here. So the distance from here to here is simply the wave speed of the aluminum times T naught over 4. So now we have, so that incident wave has moved to this point here. We then have had a part of that wave transmitted, and it's of a magnitude 1.49 times P naught. And at this time, it will have traveled into the steel a distance equal to the wave speed of steel times the corresponding time, which is T naught over 4. So that the blue line here represents the transmitted stress within the steel. We also have a reflected component, and that reflected component is right here. Okay. So it's of a magnitude of 0.49 times the incident pulse. And its front now will be at a distance equal to the wave speed of aluminum times T naught over 4 away from the interface. So this blue line here represents the reflected pulse. Now, this is now a problem of just simply linearly adding the pertinent pulses. So in the transmitted, in the steel, the only stress that's present is this transmitted one. So if we sum up all of the stresses there at T naught over 4, we get this pink line here going down and across. It's just the same as the blue line. In the aluminum, however, we now have two different stresses we need to consider. This is the incident stress, and now we have the reflected stress. And so we have to add the two of those together to get the total stress. And when we do that, we get this pink line here, steps down to P naught or sigma I, goes across, down, and across. Okay? All right. You'll note, incidentally, as you would expect, that you have equilibrium at the interface. That is, you've got a stress of 1.49 P naught both in the aluminum and in the steel. Okay? No surprise there. Are there any questions on this before I move on to make some other remarks that are only loosely related to this?
I have a question, Avi, here again. So when you have the reflected wave in the aluminum, do we expect it to have the same velocity as a wave in aluminum, or because it's reflecting back in a deformed region, would it increase?
The wave speed strictly is independent of the magnitude of the stress or the direction of stress, whether it's tensile or compressive.
Okay.
Provided the material remains linear elastic. And these two are completely decoupled. Okay. If you were to yield the aluminum, the behavior would be more complicated. Yeah. Because what you would then find is you would firstly have an elastic wave traveling at the same speed of C naught of aluminum, and then you would have a trailing plastic wave moving at a much slower speed, given by essentially the tangent modulus around the yield point, the root of that divided by the mass density. Mm-hmm. So one can readily include all of those kinds of effects by modifying the distribution in this region here.
Okay. Thank you.
Does anybody else, any of the students have questions?
I have one.
Please.
So I'm just wondering how the wave that's transmitted doesn't lose any stress, even though some of the wave has been reflected back into the aluminum.
Okay, so okay, so we are, as in all cases, all problems dealing with elasticity, and this is just a dynamic elasticity problem, we assume there's no dissipation, there's no loss. Okay? And so we normally think, if we're doing a tension test on something, on an engineering material. If we load it in the linear elastic domain and unload it, we recover perfectly the initial state. Okay? There is no dissipation. Now, if you were to look super, super carefully at the loading and the unloading curve, you might find there's a tiny bit of hysteresis. There may be friction effects. There may be some dissipation due to small amounts of dislocation motion. For most engineering materials, that's almost imperceptibly small at the kinds of temperatures that we're interested in. Okay? Mm-hmm. And so we're making the same assumption here. We're putting in a certain pressure pulse, and we're assuming that that pressure pulse can be transmitted through the material without any losses. So that this pulse here, the starting pulse, can, if this were just an aluminum bar, the shape of this pulse would keep propagating through the bar indefinitely with the same magnitude, the same shape, the same duration. Okay? Mm-hmm. And so that's the assumption that we need to make in order to analyze this type of problem. Now, as one additional sort of somewhat complicating element is this. If we do this, say, as a Kolsky impact test, so let's say we were to strike the aluminum with some other bar and put a stress pulse into the aluminum. Recall that we're assuming here that we have one-dimensional stressing. But at the contact between the striker and the aluminum, because of the Poisson straining, you have a certain amount of radial inertia. Okay? And that causes release waves to be generated from the external surfaces going into the aluminum. That then gives rise to oscillations in the overall stress strain curve. Okay, we might have seen that. Let me just return to that, just an example, because I think that this is sort of can be an important effect. So you might recall this figure here. This is of a real test. But invariably, when you measure the strains and the strain rates, you get this characteristic oscillation. And these are due to these dispersion effects. What they're telling you, essentially, is that you don't have a state of perfect uniaxial time-independent stressing. You've got these high-frequency oscillations due to these dispersions. Okay, but we're neglecting those for the purpose of this problem. Now, again, as a practical matter, if this is something that you're concerned with, if somebody wanted to do a test where they wanted a cleaner strain rate than this for some reason, then you can take certain measures to try to mitigate these dispersion effects. These are high frequency effects that you can sort of damp out by using pulse shaping material. So you can, for example, put in a thin shim of a metal at this interface here. And that will slow the ramp up to the peak pressure, but it reduces the overshoot and the subsequent oscillations in the stresses due to the dispersions. The other thing you can do, and this was actually, I think, in response to Michael's question, you can think about redesigning the bar so the dispersion effects are reduced. These dispersion effects depend on some characteristic dimension. Usually for a Kolsky bar test, it's the diameter of the rod. You can, if you really want to get rid of these dispersion effects, you can use hollow cylinders, tubes, where the dispersion effects are dictated by the thickness of the wall, not the overall diameter of the bar. Okay? So there are these measures you can take to mitigate some of these problems. But again, I would emphasize that for our purposes in this problem, we're assuming there is no dissipation. And as with all linear elasticity problems, we can always just superimpose linearly the stresses from different sources.
Mhm.
Okay,
Gotcha. Thank you.
you're welcome. Okay. All right, if there are no other questions on the assignment, I just wanted to make a couple of remarks following up on some of the sort of the themes of the questions that came out on Monday. Many of them, I think, dealt with some of the practical aspects of actually doing these kinds of tests. Now, in the slides, I'd included references to a couple of pieces of work. I didn't explicitly note them or highlight them, but I think they are extremely useful if you're getting started in this field. There is this chapter by K.T. Ramesh on high strain rate and impact experiments. It's a beautiful introductory, easily accessible article that covers a lot of the basic mechanics, and it covers a lot of the practical issues that you should be thinking about in designing or interpreting an experiment. There is another one which is more focused, more specifically on the split Hopkinson or the Kolsky bar test. That's by Rusty Gray, and that appeared as a chapter in the ASM Metals Handbook about 20 years ago. It too covers many of the basics, the basic mechanics, gives pretty concise derivations for the various relationships between stresses, strains, strain rates, and so on. And it talks about some of the practical issues associated with testing. Now, if you want to go a little bit deeper than that, or if you want to learn a bit more about the fundamentals, there is a book by Kolsky himself, published like 50 years ago now, 60 years ago now, almost. It's a little book called Stress Waves in Solids, and it is literally a little book. You can pick it up on Amazon for about $6 if you want to buy it used. It's a gem of a book. It's I think one of the best places to get started to learn about just the fundamentals of stress wave propagations in solids. All the stuff related to things that we talked about with respect to all of the conservation equations that are needed, how all of this is manifested in different types of stress waves. It's very highly accessible, I think, to somebody starting off in this field. Okay. All right. I wanted to mention one other thing, and it pertains to some of these practical aspects. And the question by Michael reminded me of this. Michael, you may recall, asked a question about maximum strain rates, maximum stresses or strains that we can get with the Kolsky bar. And I sort of gave an answer where I was hedging my bets here, saying that there's a lot of compromise that you need to think about. And in fact, a lot of this compromise is reflected in what's known as a response diagram for the Kolsky bar test. Okay, this is an adaptation from K.T. Ramesh's article. But if you look at all of the basic equations we presented last day, you can plot results of a Kolsky impact test, a Kolsky bar test, in terms of the stress that you can achieve on the specimen and the specimen strain rate. Okay. Now, what you find is that the very maximum strain rate you can impose on a specimen is simply the velocity of the striker bar divided by the specimen gauge length. That's the very most you can do. Okay? And that only happens when you have essentially a negligibly low strength of your sample. Whenever you have a finite strength, your limiting strain rate is lower. So if you put in some typical numbers here, we talked about the limiting velocity being about 50 meters per second last day. And that is because you don't want to exceed the yield strength of the striker or the incident bar. And as we noted, at a velocity of 50 meters per second, the stresses are on the order of a gigapascal. Right? So that's sort of a practical limit to keep in mind. Now, if your specimen gauge length happened to be, let's say, 5 millimeters, which is not atypical, but perhaps slightly on the short side, then that's 5 times 10 to the minus 3. So you take 50 divided by 5 times 10, 50 times 5 times 10 to the minus 3, and you get a strain rate there of 10 to the 4. Okay? So, people often talk about maximum strain rates of 10 to the 4 per second. This is essentially where that limit comes from. Okay, now, as you increase the strength of the material, the limiting strain rate is reduced. The maximum stress that you can impose on the specimen is given by this result here. So EB is the bar modulus, AB is the bar area, AS is the specimen cross-sectional area, V again is the impact velocity, and CB is the wave speed in the bar. Now, if you take a look at the quantity EB times V over 2CB, what you find is that that is equal to the stress in the incident bar. And so let's say, for the sake of argument, that that's on the order of a GPa at the highest velocity we can practically use. Okay? So we put in a velocity here of 50, wave speed of about 500, a bar modulus of about 200 GPa. Okay? So doing all of that, we get about 1,000 MPa. And so the maximum stress is 1,000 MPa times the ratio of the bar area to the specimen area. And so one of the practical ways that we can access higher stresses is by simply making the specimen smaller in cross-sectional area. So whereas the Kolsky bar might be, say, 2 millimeters in diameter and have an area of, pi over 4 times 20 squared, your specimen diameter may be only, let's say, 3 or 4 millimeters. And so this ratio can be made quite large, certainly easily a factor of 10 or greater. Okay? So you can readily, this way, access a high stress domain for the specimen itself. Now, a related issue, in addition to this trade-off between the stresses and the strain rates that you can get, is the sensitivity of your measuring devices, your strain gauges here, and the signal-to-noise ratio. Okay? So, for instance, if you're operating down in this, domain here, where you've got a very soft material, you can, in fact, get to very high strain rates in principle. But you find that because the material is weak or soft, the magnitude of the strains that reflect that strength, think of this as the strain in the transmission bar, those strains will be very small. Those are the strains that reflect the back face stresses. So if those strains get to be very small, you have problems with signal to noise ratio. And so you start to lose on the fidelity of the measurements. You can imagine up in here, if you also made this area ratio very large, then the absolute forces that are going through your bar are very much lower, and hence the strains in the bar are very much lower. And again, you have a problem with compromising the fidelity of your measurements. So one needs to think about all of these types of things in ultimately designing the cleanest possible experiment for a given material with some understanding of what the strength will be approximately and what sort of strain rates we want to access. Okay. All right.
I have a quick question.
Please.
Can you speak on the specimen material response curve and how that relates to the linear test response line?
Oh, okay. Yes. Good point. I sort of overlooked that, didn't I? Okay. So the way to think of it is this. Let's think of our material as being sort of elastic, almost perfectly plastic. It's got some yield strength, some flow stress. And we know that that flow stress depends on the strain rate once you get out to high strain rates. When we're at low strain rates, below about 110, maybe even 100 per second, this curve is the yield strength of the material is going to be insensitive to the specimen strain rate. Okay, so you're going to have a flat portion to this curve. The upturn in the strength versus strain rate curve occurs typically at strain rates of something like 100 or 1,000 per second. And then it goes up very rapidly. Okay? So what we're trying to do experimentally is to access various points on this curve. And so we ask the question, if we want to say access this point here, what sort of velocity should we use? And what sort of specimen dimensions should we use so that the stresses that we can transmit through the specimen are at least as large as this? Okay? So you could choose the conditions associated with this point here, and you could in principle apply higher stresses than you need. But of course, you won't actually exploit those higher stresses. You'll actually measure a lower stress. So this just represents the maximum stress that you can achieve. Okay? And of course, what you find here is if you do this type of calculation, you find that there is going to be some critical strain rate beyond which you can't actually probe your material response. That is, when you hit it, when you test it, you find you don't get into the plastic domain. You just have an elastic response.
Okay. Thank you.
You're welcome. Any other questions?
Hi, hello. So I have a couple of questions.
Yeah, go ahead.
So first is that, so for the string curve on the slide, because so basically is that for the dynamic experiment for the cost, for example, for the Kolsky bar, that the velocity is the applied boundary condition. That's the I mean, not the strain or stress, and then the stress and strain are calculated from measured strain or our measured Young's modulus as a prior, and then we got the so-called stress strain curve. So first, adopt the definition of stress and strain, and of course the definition is correct, but how people can measure accurately the stress and strain, especially in such a short time, and also the area of the specimen may also change a little bit. So could you please comment on that? Thank you. That's the
okay. Okay. So measuring the stresses, I mean, what you're essentially doing is computing the forces. And you get those forces, as you suggested, using the strain gauge. That gives you the strain in the bar. You know the area of the bar, and you know the Young's modulus of the bar. So that gives you directly a measure of the force being transmitted through the bar. Now, depending on whether you're calculating the stress on the back face or the front face of the specimen, you use either the strain in the transmission bar or the two strains in the incident bar. The two strains in the incident bar being the incident strain and the reflected strain. Okay? Now, so we know we can measure those forces accurately. Now, we assume that we know the cross-sectional area of the sample to begin with. And you're spot on when you say that the area of that specimen will change as it's deforming plastically. Provided the deformation is volume conserving, and in most metal deformation problems, that's a very good assumption, then you can use volume conservation in combination with information about the axial strain on the specimen to compute the instantaneous cross-sectional area. Now that assumes, of course, that the cross-sectional area changes uniformly along the entire length of the specimen and that there are no friction effects. Right? So you can make, you commonly will make a correction to the area of the specimen, which will depend on the strain that you put into the specimen. And that's a very easy and straightforward adjustment to make. Now,
Okay.
Again, this assumes that everything is uniform within the specimen. If you have any kind of localized behavior where your strains are not uniform along the specimen, then you have problems. You can only compute sort of the average or parent strain and strain rate, not the actual true local value. Okay. All right. Now, was there another part of the question? Can you?
Yeah. So I also got a couple. So
yeah.
And then that what is a typical time for a dynamic test, like for the Kolsky bar or the indentation? Test.
For the Kolsky bar. Okay.
Right.
So, okay, let me just go back to something. Go back to basics. Okay, so the time scales. So think about the physics here, the mechanics. You have a striker bar, it hits this interface here. This stress pulse, you have a stress pulse in the striker that goes from the interface back into the striker, and you have a pulse going into the incident bar. The pulse in the striker reflects off the back face, comes back as a tensile wave, moves forward, and at that point, once the wavefront has reached this interface again, the stress in the bar and the strain in the bar will go to zero, because the reflected tensile wave on the back face perfectly cancels the compressive wave, the incoming compressive wave. So the time associated with that is simply, it should be on the slide somewhere, it's twice the length of the bar.
Okay.
Divided by the wave speed within that bar. Okay. Now, typically, if you put in dimensions of striker bars that are usually used and the wave speeds of steel, about 5,000 meters per second, you find that this time is on the order of 100 microseconds. Okay.
Okay. Okay.
Or a few hundred. And actually, if you look at this data here, this is real data. I can't remember on what material, but the durations of the loadings are on the order of hundreds of microseconds.
Right. Yeah. Thank you.
Okay.
So, a follow-up question is that given such a short time, how does the strain rate affect the response? So actually, the motivation for me to ask this question is that because you mentioned the Dashbandi Fleck constitute relation, and also you mentioned the Dashbandi Evans constitute relation as well. So one of them is rate-independent plastic response, and the other is viscoplastic response. So because given such a short time, because usually whenever I encounter a rate-dependent elastic plastic response, usually I'm thinking about the creep response that will be for a long time. So for such a short time, first question is that okay, probably one by one. Okay, so first is that can you recognize a material, whether it's a strain rate sensitive material or not, from the dynamic experiments, like from the practical side? Can you first? Thank you.
Okay. So I think, the question you're asking pertains to the mechanisms of inelasticity and the sensitivity of those mechanisms to strain rate.
Mm-hmm.
So, when you're at low strain rates in the creep domain, typically below about 10 to the minus 6 per second, the mechanisms will often involve diffusive processes.
Right.
Where you can get, for example, if you're at very low stresses and long times, you can get vacancy diffusion or self-diffusion from between boundaries, grain boundaries. And this is the so-called Navarro herring or the Coble creep type mechanisms. And these mechanisms are slow. Okay? Transporting matter by diffusion is very slow. When you get up to higher stresses, you find that dislocation motion itself, even by glide, depends on thermal energy. The more thermal energy you put into the system, the easier it is for dislocations to bypass obstacles in the lattice. Okay? Right. So when you go from the very low stresses, you find there that the material behaves essentially as a Newtonian material, where the stress is proportional to the strain rate.
Right.
Okay? When you get into this other domain where the dislocation motion dominates, you follow a more complex power law relationship between stress and strain rate.
Yes. Mm-hmm.
Then there's a temperature regime and a strain rate regime over which that sensitivity is lost for a number of reasons. For example, if you have an FCC material, you find that the intrinsic lattice resistance is small, and that the barriers to dislocation motion, the thing that makes FCC material strong, are things like dispersoids or precipitates. These are long-range types of obstacles, and it's difficult for them through thermal energy for dislocations to bypass those obstacles. We can think of those types of obstacles as being athermal. And if it's athermal, the implication is that they're strain rate independent, the very least
Right.
strain rate insensitive. Okay?
Right.
So with FCC materials, you do find there is this extended domain in strain rate where the strength is essentially constant. Now, when you go to BCC materials, the situation changes. There, because of the nature of bonding, the lattice resistance itself is important. Okay? The intrinsic lattice resistance, or the pile stress, whatever you want to call it, in BCC materials is typically 1 to 2 orders of magnitude higher than it is in FCC materials, everything else being equal. And so, if you look at things like steels get a lot of their strength just inherently from the lattice resistance of iron. Huh? You can't say the same thing about a copper alloy or an aluminum alloy. Copper and aluminum in pure form have yield strengths that are, in the low single-digit megapascals. Huh? Whereas with steel, with iron, it's in the range of maybe 100 or so, 150 MPa. Those kinds of materials where the lattice resistance is important, and recognizing that the lattice itself represents a short range type of obstacle, those obstacles can indeed be overcome through the addition of thermal energy. And so those materials you'll find exhibit a stronger temperature sensitivity as well as a stronger rate sensitivity. If you look at the mechanics of those mechanisms, you find that the strain rate sensitivity and temperature sensitivity go hand in hand. Now, taking this out to even higher strain rates, what you find is you get into domains where you have phonon drag mechanisms that operate. This is at very high, this is at strain rates of about 10 to the 3. They're not super high, but they're high. Where it becomes, you're starting to kick in other mechanisms that retard the movement of dislocations. Now, if you want to take it to an extreme, now, by the way, those phonon effects, they're going to be present in all solid engineering materials. Okay? So you'll find invariably that all engineering materials, when you get beyond about 10 to the 3 per second, they're all going to exhibit quite a high strain rate sensitivity. Now, as you go up to even higher strain rates, what you find is that the displacement rates, the speeds of dislocations, are now starting to approach the shear wave speed in the material.
Right.
And so the shear wave speed is essentially a limiting maximum speed at which dislocations can move, because that's the fastest that you can transmit shear information about shear waves in the solid. Okay? And so what you find as a result when you get into this very ultra high strain rate domain is that the flow stress then starts to, or the stress versus strain rate plot starts to plateau. Okay? And that again is true of virtually all materials.
Okay, so basically you have explained to me that the strain rate with different values of strain rate and time with various deformation mechanisms.
Yep.
And with the strain become higher and higher, there's a plateau for stress because of the limit for the dislocation to move. And
Yes.
so basically the question I asked is that from the experimental response, how do people recognize a material is strain rate sensitive or not? So from your answer I got is, so it's really up to the range of the strain rate and also the type of materials. May I explain this as this?
I think so. Let me perhaps paraphrase it to make sure I understand the point. As a practical matter, the way you assess strain rate sensitivity is by, depending on the domain that you're in. Let's say we're in this dynamic domain, not in the creep domain. If we're in this domain that we're talking about here, that we're illustrating here with a Kolsky bar, the way you probe rate sensitivity is simply perform experiments at different strain rates. And the main parameter you vary to change the strain rate is the striker bar velocity. Okay. And so you can measure the stress strain response at various strain rates. And from that, you immediately see the degree to which the material is rate sensitive.
Okay. So one more question. Just a follow question to your just the sentence you said. So when we increase the velocity, yes, we increased the strain rate, but we may also increase the stress or strain. So with that, there is also strain hardening effect come into play. Is that correct?
Oh yeah, absolutely.
Right. So
yes.
So when different mechanisms come to play together, how to distinguish them, or say
Okay. Okay. So now you're digging into some really interesting questions. That pertain to the combination of strain rate sensitivity plus strain hardening. Okay? And when you're talking, as I mentioned before, when you're talking about rate sensitivity, there's always a temperature sensitivity that goes hand in hand with it. Here's a collection of results from one of Rusty Gray's review articles showing the different types of sensitivities in BCC, FCC, and CHP types of metals. Okay. And so what you find is, if we just look at room temperature results, let's say we compare for copper, this is the prototypical FCC material. There's a test here, this green test is at 0.1 per second, it's a quasi-static result. This other result up here is at 2000 per second. Okay? And now what you find there is, if you have essentially pure copper, and this is in fact pure copper, your yield strength is almost zip. It's on the order of a couple of MPa. Okay? And what you find is that strength doesn't depend on strain rate. The material, however, exhibits a very high strain hardening rate, as manifested in this green dotted or dashed line. Now, when you go to higher rates, you find that the degree of strain sensitivity or the strain hardening does depend to some extent on the strain rate. Right? Now, in other materials like tantalum, this is a BCC material that's of great interest to people. You find that when you go from, let's say, okay, we have the green and the red here. This is at 0.1 per second. The red is at 1300. What you find in this case is that because this is a BCC material, the yield strength itself is very strain rate sensitive. So in this case, you're going from a yield strength of about 300 MPa to a yield strength of about 550 MPa. Okay? And that's true of most BCC metals. Interestingly, the strain hardening in these materials doesn't change very much with strain rate. Okay? Now, the other thing you'll notice here is, as I mentioned, the strain rate sensitivity always comes with a temperature sensitivity. And so when you look at higher temperatures, or let's say you're at 800 degrees C, you'll find at a high strain rate, you will get a reduction in the flow stress. Conversely, if you go to low temperatures, even if you're at low strain rates, you may get a very high strength. Okay? So this, as I say, so when you have a high strain rate sensitivity, you have a high temperature sensitivity. Zirconium, it's sort of a hybrid in some sense. It's a bit more complicated with CHP, close packed hexagonal materials. And you can get some sense of the rate sensitivity and the temperature sensitivity from the results here for zirconium.
Okay, thank you. So basically, is that in order to distinguish the contribution from this different mechanisms, we have to be careful with the materials we picked that to study this effect. Is that correct? So yeah.
Yes.
Okay.
Yes. Well, I mean, you can certainly study the effects experimentally, but if you want to understand where the rate sensitivity is coming from, where temperature sensitivity is coming from, you need to think about the mechanisms that are operative.
Right. Because for a practical case, is that, for example, if we would like to characterize the strain rate exponent or strain exponent, that from this experiment that we have to be careful, because for many of the materials, the response are a combination of these two exponents. So it's not simple to get this two exponent from one type of test to say, because it's a combination. So that's one thing that this dynamic experiment cannot in terms of the characterization. May I say this?
Well, if you do experiments at different strain rates and at different temperatures, what you find is that there are now pretty robust material models to describe different mechanisms and their rate and temperature sensitivities. And I think this article by Rusty Gray talks about some of them, if not in this particular article, in some other articles that review articles that he's written.
Okay.
But there are rather robust micromechanical type models to describe these sensitivities. And so what you do then, as a practical matter, is you use data of this type to either calibrate or assess the model itself.
Okay. So basically, that we take this stress strain curve from experiment as the input in the FEM model or the micromechanics model, and then we calculate the corresponding response and then compare with the experimental data, and
things
then
like that. Yeah.
To feed this to get the experiment. Okay.
Yep.
Okay. Thank you so much. Thank you.
You're very welcome. All right. All right.
Any more questions? I thought I heard somebody saying there was a question. If not, thank you so much again, Professor Zok, for this review and going over all the details and the questions and stuff. I hope the rest of us, everybody, I hope you have a good weekend, and we'll log in again next Monday for the next lecture. Thank you so much.
Thank you, Avi. Thank you all for sticking around and for asking very good questions.
And this was a great review. Thank you so much.
You're welcome. We'll see you all later.